Thank you, Chairman. I'd like to thank committee members for giving me an excellent opportunity to present our recent works. The title of my talk is Mid-Infrared LWIR, whose wavelength is around 10 micrometer, that is equivalent to 1000 Kaiser. Passive spectroscopic imaging for medical measurements, like non-invasive blood glucose sensor from a distance. This is Ichiro Ishimaru, Kagawa University, Japan. This work was published last November in Scientific Reports. The title of this article is Glucose Emission Spectra through Mid-Infrared Passive Spectroscopic Imaging of the Wrist for Non-Invasive Glucose Sensing. If you are interested in our study, please download this article and read it. Scientific Report is open access journal. Download is free. We have been trying to introduce mid-infrared spectroscopy into daily life environment. As you know, Fourier transform infrared spectrometer, so-called FTIR, has high ability for component analysis, but apparatus is relatively large and expensive. So we believe downsizing and price reduction will realize healthcare sensors in everyday life, like non-invasive blood glucose sensor. We have made two types trial products of a proposed Fourier transform spectroscopic imager. One is two-dimensional imaging type that is a kind of temporal phase shift interferometer. And another one is one-dimensional one-shot type that is a kind of spatial phase shift interferometer. As for two-dimensional imaging type, we could acquire two-dimensional spectral distribution within several seconds or around 10 seconds. We realized palm-size apparatus using uncooled microbolometer array sensor. Uncooled microbolometer array sensor is used for thermography. This palm-size apparatus could be mounted on drone. In the case of one-dimensional one-shot type, we could obtain one-dimensional spectral distribution on the line within frame rate, like 15 milliseconds. We constructed the Pierce-sized apparatus that could be built in smartwatch. This apparatus could be operated by notebook PC. So total system is very compact. So portability is very high compared with a conventional hyperspectral camera. This conventional technology, product name is HyperCam, that is provided by Telops Corporation. We proposed imaging type two-dimensional Fourier spectroscopy that is a near common pulse interferometer. So proposed method has strong robustness against mechanical vibration. So we realize downsizing and price reduction without anti-mechanical vibration systems. Towards 6G world, we want to realize super smart society watching by invisible light, I mean infrared light, casually. Not only for the non-invasive blood glucose sensor, smart room, smartwatch, smart toilet, but also we want to apply our method to identification of microplastics and soil analysis, or identification of gas species on broad area, and visualization of concrete damage levels. Using this figure, I'll explain the principle of a proposed imaging type two-dimensional Fourier spectroscopy. From the optical point of view, object plane is covered by many bright points. I mean, bright points aggregation. For example, from a single bright point, rays are emitted to the multiple directions. These emitted rays are collimated by object lens and concentrated into single point by imaging lens, and conjugate bright point image is formed on imaging plane. Of course, there are many bright points on the object plane. These emitted rays are concentrated into the different coordinate on imaging plane. That is the conventional infinity-corrected imaging optics. We installed new optics as a half-flux of object beam that is called variable phase shifter. Variable phase shifter give an arbitrary optical path difference onto the half-flux of object beam. If half wavelength optical path difference given to the half-flux of object beam, upper beam and lower beam weaken each other as interference phenomena, imaging intensity increases. If single wavelength optical path difference given to the lower flux of object beam, upper side and lower side strengthen each other as same as initial state. So imaging intensity increases. So we could confirm the cyclic imaging intensity changes in accordance with optical path difference. This graph shows if we use the monochromatic light as a light source, but for spectroscopy, we use the polychromatic light as a light source. As for the long wavelength component, imaging intensity changes in low frequency. In the case of short wavelength component, the cycle of imaging intensity becomes to be short. Some of these cyclic cosine waves form the interferogram. And these interferograms are detected on every pixels simultaneously. As I said before, this interferogram consists of multiple cosine waves. So we could acquire the spectral characteristics by mathematical Fourier transform algorithm. We configure the variable phase shifter by fixed mirror and movable mirror. This movable mirror is actuated by ultrasonic stage. So we constructed near common path and wavefront division interferometer. Please look this movie. Inside of the apparatus is very simple. Object lens, phase shifter, and imaging lens, and uncooled microvolent array sensor. We used boson provided by Fourier Corporation. And we mount this apparatus onto multicopter type drone. At this time, total weight of our apparatus was 1.7 kilogram, including a battery and a controller. we used Raspberry Pi as a controller. We successfully observed the mid-infrared image, spectral image from 15 meters above the ground. We could verify the strong robustness against mechanical vibrations. And using this figure, I'll explain the principle of one-shot type spectroscopy. Instead of the mechanical phase shifter, we installed relative inclined phase shifter. Relative inclined phase shifter is configured with cuboid glass and wedge glass. The inclination of wedge glass is around 1 degree. At this time, horizontal axis on imaging plane correspond to the optical path difference. So we could obtain interferogram as a spatial fringe pattern. And the vertical axis of imaging plane is equivalent to the coordinate of imaging line. So we could obtain one-dimensional spectroscopic image from one frame data. That's why this method is called one-shot type or the snapshot type. And we also integrate relative inclined phase shifter and imaging lens into one optics. So only 2 optics are enough for configuration of one-shot type. Diameter of object length is 6 millimeter, and the optical path length is around 15 millimeter. That will be built-in smartwatch. Please watch this movie. Almost all is sash. Inside of silver sash, maybe you could recognize a small lens whose material is germanium and the diameter is 6 millimeter. From now on, I will explain the passive spectroscopy. As you know, some graphy detect radiated light emitted from body heat. Body temperature is around 300 Kelvin. This photo shows the mid-infrared image of human arm. Our question and curiosity is, radiated light include body components information like glucose. Sonography is based on Planck's law. Spectral emittance of black body is determined these curves. Horizontal axis shows the wavelength and vertical axis shows the emittance. And the body temperature is around 36 Celsius. That is approximately equivalent to 300 Kelvin. The integrated value of these curves, I mean area, is converted into temperature, and the temperature is displayed as false color image. This is thermography. But originally, these emission light derived from molecular vibration. And each molecular structure has specific resonance frequencies. The emission spectrum, due to the intrinsic vibration of molecules, have emission peaks. In this picture, lambda 1, lambda 2 for each component. We expected Internal body components like glucose will be estimated from emission spectrum. And then I'll explain the differences between active and passive spectroscopy. Active spectroscopy is the general mid-infrared spectroscopy using light source. But for passive spectroscopy, we do not use the light source. Measurement unit detects the radiated light of object temperature. In the case of active spectroscopy, light source illuminates the target and the measurement unit detects the reflected light. At the time, molecular vibrations are excited by illumination, and light energies are absorbed as vibrational energies. A spectral absorbance corresponding to the molecular structure is acquired. But for passive spectroscopy, we do not use the light source. Measurement unit detects the radiated light from the target, derived from molecular vibrations. Compared with the active spectral absorption, at the same wavelength in this figure, lambda 1, lambda 2, we could confirm the emission peak at the same wavelength, lambda 1, lambda 2. So, active and passive spectroscopy has a negative and positive relationship. And this photo shows the experimental setup for non-invasive blood glucose sensor from a distance. We set a rest at a distance from spectral imaging device 600 millimeter. And these data shows the measurement results obtained from the object. On the right-hand side graph, black solid line shows the spectral absorbance previously measured by FTIR. We use the glucose solution as a sample and measured by conventional FTIR. This is active spectroscopy. And we could recognize the specific absorbance peak of glucose solution at 9.25 and 9.65 micrometer. Red solid line show the spectral emittance observed by our proposed method. At the same wavelength at 9.25 and 9.65 micrometer, we could recognize the specific emission peaks. So we could confirm the negative and positive relationship between active and passive spectroscopy. And this fourth color image shows the emittance map whose wavelength was 9.65 micrometer. Mid-infrared passive spectroscopic imaging successfully detects glucose components from rest. And then we compare the time series changes of blood glucose concentrations compared with conventional blood collection type. This graph shows the measurement results taken every 10 minutes from 0 to 60 minutes with the conventional blood collection type. Around 15 minutes, the subject drank drink containing sugar. Blood sugar level gradually increased from 100 milligram per deciliter to the 140 milligram per deciliter. This is the conventional method. And this emittance map shows, false color image shows the emittance map whose wavelength was 9.65 micrometer. And the numbers at the bottom of false color image show the glucose levels measured by conventional blood collection type. Blood glucose level gradually increased from 101 milligram per deciliter and reached to 106.8 milligram per deciliter. And the emittance map changes to yellow color. Yellow indicates the higher emittance than green and blue. The emittance map changes to yellow as the blood glucose level rises. We demonstrated the feasibility of non-invasive blood glucose monitoring from a distance. And this graph shows the time series data of spectral emittance of subject. Blue solid line shows the blood glucose level measured by invasive collection, conventional invasive type. And the red solid line shows the average emittance whose wavelength was 9.25 and 9.65 micrometer. These two graphs do not overlap because the unit of the vertical axis, emittance, and invasive blood glucose are totally different. But we could confirm there is a strong correlation between these two time series data. We conducted similar clinical trials on 5 subjects. In addition, these clinical trials were conducted in accordance with a protocol approved by the Kagawa University Ethics Review Committee. And we plotted all data on Parkes error grid. Horizontal axis shows the blood glucose level measured by the conventional blood collection type. And vertical axis shows the blood glucose level that is converted from emittance using standard curves. The unit is milligram per deciliter. 91% of data are in zone A. Other 9% of data is zone B. As for US FDA, if 99% of data in zone B, the device can be approved as a medical device. However, the number of subjects must be increased. And we measured emission intensity of various body parts: iris, arm, forehand, back of hand. At every body pulse, we could recognize the emission peak at 9.25 and 9.65 micrometer. We propose healthcare sensor casually watches over people with invisible light. AI speaker with built-in passive spectrometer will be placed on dining table. It will casually measure the blood sugar level of several people around the dining table simultaneously. And complementary, we wear the smartwatch for outdoor use. It is easy to integrate these healthcare data on the internet. We have 5 related topics on this conference. After my presentation, Ms. Tahara will make presentation on visualization of glucose omnipresence based on time response differences. She paid attention on the time difference between blood collection type and freestyle relay and our method. She successfully extracted the vein area from mid-infrared spectroscopic image. And many audience have a question, maybe. From what depth are radiation light emitted? In other words, what depth component can passive spectroscopy measure? Mr. Anabuki made emission propagation model inside skins, and he clarified the depth problem. Very interesting presentation. And Mr. Yano will present on Broadman, whose wavelength 3 to 20 micrometer, reflective optics spectroscopic imager with uncooled microbolometer array sensor. Lactic acid levels whose emission peaks are 5.65 micrometer are an indicator of fatigue. And ketone bodies whose emission peak are 4.65 micrometer are an indicator of metabolic effects of dieting. And other 2 presentations were finished yesterday, unfortunately. Mr. Yamashita made presentation of mid-infrared passive spectroscopic imaging for visualizing tooth hardness. And Mr. Miyamura presented you mid-infrared passive spectroscopic imaging for monitoring food composition. He visualized the fermentation process of Japanese sake and agricultural field. If you are interested in their study, please ask them at coffee break. Thank you for your kind attention.